Just a bit of background before we get into the presentation about who I am and what MBDA are. I'm a technologist, which means I dabble in lots of things but don't get involved directly and deeply into any particular project. I've been working with real-time embedded systems for too many years across a vast range of projects. 25 years of that have been with Ada, more than 15 years with Spark, so this isn't new to me, I'll put it that way. MBDA itself is the #1 European guided weapons defence contractor, spread across UK, France, Germany, Italy. There's a bit of a presence in the US, and there's a very small presence in Spain, so quite widely spread. We develop a wide range of products from mission planning through mission control, command and control systems to embedded missiles and missile subsystems. So we do things from the very soft kind of systems through to hard real time. First thing is a question to you lot. How many people are actually using autocoding? Have a show of hands, please. Oh, there's a few, not everybody, but a few. I'm sure it'll get more in time. My goal of this talk was really to provoke some discussion about autocoding and what it means in terms of software design and how we can best use it. It's really questioning this sudden kind of rush to autocoding that seems to have occurred over the past, I suppose, 5 to 10 years. I could have entitled this talk something like Autocoding, the Emperor's New Clothes or the Silver Bullet, but I think focusing it back on software design is a little bit more appropriate at this point. We'll come back to the other definition towards the end. I'm not expecting people to agree with my viewpoints, by the way. They're mine, they're not the company's, but we'll see where we go. Right, so the contents of the talk. I'll start off by saying why I wanted to talk about autocoding and what I think the issues are with it. Move on to what I mean by autocoding. I expect we've got some slightly different views around the room as to what actually autocoding is. Then I'll look at what we do in terms of design in a traditional software development process. What is the role of design? How does design work in that environment? And then kind of contrast that position with one that seems to be emerging for autocoding. Certainly within my company, that's the way it's emerging anyway. That throws up a number of problems, which I've kind of got to propose a possible solution towards those, to getting rid of those problems. And this being the Spark user group, we've got to have something about the role of Spark in that solution. And there is a role for Spark in the solution. I then briefly cover an example of actually how you can implement this. And it's not a theoretical example, it has been done. I'll cover it briefly. It's quite a long thing in its own right, though. And then some thoughts about where the future will take us with autocoding and some final conclusions and time for questions. So, why? Why talk about autocoding? Well, it's becoming all pervasive. Certainly, over the past few years, it's rocketed into existence within my own company's domain. We use autocoding in a vast number of areas for various different things now we didn't use 5 or 10 years ago. And this is kind of bringing in some other things that maybe weren't obvious to the people deciding they'd use autocoding. Engineering disciplines are changing dramatically. The people who used to be responsible for the software architecture were software engineers. Now there's a lot of other players in that. There's a lot of systems engineers dabbling in it. There's control engineers. They're all getting involved in the software architecture. And this happened pretty unwittingly. There's a lot of architectural decisions being taken by people who are not software engineers. And there seems to be a bit of a movement away from worrying about how you engineer the implementation on the target. The software designs we create are becoming embedded in other tools. So the notations of the tools and the way in which the tool generates things are taking over some of the design aspects from us. And while there's a lot of dimensions to a design, there has to be a question about can an autocoding group address all the dimensions, the non-functional dimensions as well as the functional ones. And then you get the question, well, what does the autocoding actually address? What doesn't it address? And I suppose in some cases, people might ask, well, does it matter if we know what it addresses? I think the answer to that is probably yes, because we spent a lot of time over the past 20, 30 years of software engineering worrying about design. To not worry about it now would seem to be quite strange. I'll look at this by reflecting on the role of software design in the past and how we might see it working in the future in an autocoded environment. But first, before we look at that in detail, some myths. Right, the first one is, this is the myth of The detail doesn't really matter. If we've got more processing power, we can handle anything. It doesn't matter how inefficient the code that's generated is. The processing power will eventually accommodate it for us. We know that's going to be the case, because that's the case. It's been true for the whole life of computers, effectively. The second one is we can get more functionality if we've got faster processors. The more processing capacity we've got, the more we can add to the product. That's the salesman's viewpoint. We can sell this product. We created it 5 years ago. Surely we can add more functionality now by increasing the processing capacity. Autocoding shortens product development times. That's the only one of those which is truly only related to autocoding, but it's a very important one. It's the one that says, well, if we don't have a coding step, we can reduce the timescales and costs. And I think some people also think they can remove the step in the process that introduces all the errors, the one that does this manual transformation from a requirement to code, the point where error is introduced. We'll come back to those later anyway. Right, what do I mean by autocoding? I think the first bullet really says what I'm trying to say. It's the generation of a level of code from some form of model without human intervention. I don't want to get hung up on what a model is. It can be almost anything. It's a fairly open view. The whole range of autocoding technologies available. There's what might be described as old-fashioned software computer-aided design type approaches where you generate skeletal frameworks which you've populated with functional elements written in some high-level programming language. These are very programming language dependent generally. There's models defined in terms of proprietary structures. You get code generated in a not very open manner. This is quite often the control engineering type tools are like this, so the MATLAB Simulink and things like that generate this kind of code. It's usually very low-level code at the end of it, usually C. And then there's the kind of the extreme, the most modern way of looking at it, I guess, is the mixture of graphical and textual inputs, the UML, executable UML approach, which is entirely source language neutral from a traditional computing viewpoint, and where you get translation of these notations into some application. The MBDA approach, where we've got platform-independent models and platform-specific models, and we're translating between the two effectively. The degree of openness for these tools varies, I think, to an extent, depending on how much you're willing to pay, in fact. We mustn't get hung up too much on the programming language, even though in some cases it's critical. But in general, we can generate almost any language we like. We could have a VHDL for firmware for FPGAs, and we could have different languages for different parts of the application if necessary. It's not something to worry about too much at this point. So looking at the traditional approach to software development, what we've got is basically a design element where we're doing many layers of design, producing basically various artifacts at that level. There's some transformations between the layers in here. Some of them are automatic, some will be manual, some will be well-defined, some will be ill-defined, basically because the traditional software development approach is based on people's skill and experience. It's not based on a tool transformation. Ultimately, we get down to some source code, which in its own right will have design information in it potentially. In terms of, if it's a very low-level language like assembler, clearly there's no design information in it as such. But if you look at something like Ada, there's packages, there's tasks, there's subprograms. You've got different levels of abstraction within the source code. And then we've got the final step, the compilation step, the traditional step to the object code. I think generally everybody accepts now that the object code is almost an opaque artifact of the process. We don't question what's in the object code too much, because actually we don't have very many people who understand what's in the object code. We don't have many experts in that domain. So we got, through the layers of the design, we've got multiple abstractions, we've got functional and non-functional, and we do worry about timing, security, safety, reliability, how resources are being used, how much utilization you've got, what spare capacity we have. The layers support all these separations of these different concerns, and between the layers there's fairly low coupling, we hope, and there's high cohesion within the layers. It's all the good software engineering disciplines that have been developed over many years. I said the source code is not a single layer. If you go back to the original kind of early developments when we had assemblers, there was very little abstraction in the assembler language against the object code. You just didn't have to know what the ones and noughts meant in the assembler language, basically. And so refinement from there to there allows us to optimize the solution. We don't tend to, in a traditional approach, include things that aren't necessary or aren't desirable. We try and remove them. Because in the end, we have to test them, and we find that things get in the way. Things that we got there we can't test, we tend to remove in the end. If we go on to an autocoding approach to the same kind of thing, it all looks very similar. We've got a design phase in the top where it's all done in tools, but the layers are less distinct. And if you've got the skeletal framework approach, it does expose some of the detail, but not necessarily very much of it. Depends on how much is in the framework and how much is in the algorithm. The source code is really just an internal and unmaintained artifact of this. It's no longer something that anybody considers in any considers in any great depth. And so we get the standard compilation process from this opaque source code into some opaque object code. Perhaps really it's better viewed like that, where we get the translation is to the source code. Now, what we've done now is we've made a very big step from the model to effectively the product we're going to run. We're not worried about how the source code is translated into the object code as much as we used to be. We're not worried, but we've got a big step from in the translation to source code. And whereas the translation from source code to object code is well understood, there's a lot of work being done on compilation technology. It's a well-founded part of computer science. The translation from models, which have got somewhat more bespoke semantics and tool-centric semantics, to some source code is less well-defined in general. So we end up with very little non-functional abstraction in the design because the design is looking fairly fundamentally at functional issues. Partly that's down to the fact that the people actually creating those models actually are mainly concerned with the functional aspects. They're not so concerned with actually how the thing executes. They want it to execute within a given time, but how that's achieved is not their normal concern. Their concern is they achieve the correct level of stability or control in a control law. There's an issue to do with the domains of these systems. The non-functional properties are heavily influenced by the domain of the product, but the tools all look at the domains of the engineering domains they're targeted at, not the products. So where we would normally do a software design that was specific to a particular kind of product, the tools are actually looking at software design that is particular to a particular engineering domain, like control engineering or something like that. So we're missing some things here to do with how we get the product domain information back into the design. And the product domain information is the important thing that ends up in the design, because we're trying to produce a product in the end, not just a simple design. Through the use of these tools, there's not much opportunity to optimize the design into the object code. The optimization really requires you to actually understand the domain and actually the product domain and actually know what you can and cannot simplify. But it's very difficult to embed or overlay that on some of these tools, very difficult. I don't think it's possible to overemphasize the importance of the product domain. The tools are not product domain specific. Most of them are designed for an engineering domain, which is not a product as such. It's a small part of a product they'll be addressing.